to ask yourself whether you've got to name it or give its formula is it ionic or covalent, right? So always look at the first element. The first element, look at the periodic table. If it's to the left of the zigzag line, everything except for hydrogen, remember hydrogen really should be over here, but everything to the left of the zigzag line is a metal, and if you see that, then you know it's ionic, okay? So for the first one, like looking at iron, so you find iron on the periodic table, and so there'll always be ones that you know the names and formula, the names and symbols for. I won't ask you ones that you don't have to know anyways, but you find iron, see that it's to the left of the zigzag line, that's how I know that's ionic. Looking at the second one, calcium, calcium's over here, so that's why I know that that one's ionic. So just look at the first element in the formula or the name, and if it is to the left of the zigzag line, then you know that it's going to be ionic. So then the next one, S4O2, so you find S, the third one right here. So if you find S, and you see that it's to the right of the zigzag line, then that is your nonmetals and hydrogen, and that's why it's covalent. So really you want to do this part first to determine if it's ionic or covalent, because remember, that's going to determine how you name it. If it's ionic, you use the whole name of the first element, first part of the second element, plus IDE. If it's covalent, then you have to do the whole name of the first part of the second, plus IDE, but you got to go back and add the number prefixes. So remember that covalent keeps those number prefixes. Covalent has to have the number prefixes. Remember that that's mono, di, tri, tetra. You have to name both of them, right? You have to name how many of the first element, how many of the second element. If the first element's only one, you don't have to use mono. But under all other circumstances, like for S4O2, that is tetrasulfur because it's 4 sulfurs. So you see this one? It's a covalent molecule. I put sulfur and I put oxide, but I got to go back and add those number prefixes to indicate how many of each. Only for covalent. You do not use number prefixes for ionic.
You said, what about the mono just now?
Mono, I don't have to use mono if it's the first element to only one. Like CO2, you just say carbon. I don't say monocarbon dioxide. I don't have to use mono if the first element is one, but if the second element is one, I do. Right? So you always give the number of the second, then you use the number for the first if there's anything other than just one. So that is why this is tetrasulfur. Tetrasulfur means 4 sulfurs. Then dioxide tells you 2 oxygens. Okay, so you might find it easy to just like say the whole name of the first element, first part of the second element, plus the IDE. If it's covalent, go back and add the number prefix there. Okay, they have to have number prefixes. Ionic, no number prefixes. Because ionic is only going to combine in one way, because you get a positive charge, negative charge, you swap the charges, that's the formula, right? So you don't use any, there's not multiple ways they can combine, there's only one. So remember that whatever your metal is, it's always a positive ion. Whatever your non-metal is, it's always a negative. The metal is positive by its group number. The non-metal is negative by 8 minus its group number. So like if you're looking at oxygen, it'd be 6 minus 8 minus 2, right? Or 8 minus 6, either way. Nitrogen's in group 5, so 8 minus 5 tells you it's a negative 3. The non-metals with ionic will always be negative. The metals are always written first. They're always positive. The metals are always written first, and they're always positive. They are the group by their group number, right? So everything in the first column ends up with a +1. Everything in the second column ends up with a +2. Non-metals are negative by 8 minus their group number, right? So so nitrogen and phosphorus are -3. Oxygen and sulfur are -2. Fluorine, chlorine, bromine, and iodine, they're all what? They would all end up with a -1 because 8 minus 7, right? So that would tell you the negative number, right? So remember, your metals are always positively charged by their group number. Your non-metals are always going to be negatively charged by 8 minus their group number. And there's only one way they can combine. So you can't have NaCl or NaCl2 or NaCl3. They don't exist that way because they form ions and you swap those charges. So there's only one way they exist. That's why you don't use number prefixes. But do remember that you have like the two oddballs that you have to remember. Those transition metals, you have to use the Roman numeral. And the polyatomic ions. And remember, you just use the whole name of the polyatomic ion if it's in the molecule. You want to make sure that you can recognize the polyatomic ion if it's in the name, as well as recognize it in the formula when you have to give the name. So that's kind of like the first one. So the first one is an example of where I have the transition metal. Remember, iron, chromium, and copper, those are the only three. So when I look at the first one, so I'm talking about this one right here, looking at the first one, iron 3 sulfide, I have that Roman numeral because the Roman numeral tells you what? It doesn't tell you how many iron, it tells you the charge on the iron, right? So iron Roman numeral 3 tells me it's iron with a +3 charge. Okay, that Roman numeral right here tells me what this charge is. So, because iron can be +2 or iron can be +3, that's why I look at what that Roman numeral is. So that tells me what the charge is. I know the charge on the sulfur because it's over in group 6. So 8 minus 6 tells me it's a -2. Notice the first element's positive, second element is negative. When I swap the charges, it gives me the formula of Fe2S3. Okay, so that's the transition metals. I gotta have the Roman numeral. It tells me what the charge is. Second one in this example with the calcium and the NO3. So looking at this one right here, what you've got to be able to recognize is you've got to look at NO3 and say, that's a nitrate. Okay, that's not a nitrogen oxide or something like that. You've got to recognize that that NO3 group with the metal out front is a polyatomic ion. So you use the whole name of the metal, calcium, and then you just use the name of the polyatomic. So that's why it's calcium nitrate. No numbers, prefixes, don't need any Roman numerals because there's no transition elements in that one. It's just calcium nitrate. All right, so let's look at the fourth one down. So we did those three good examples and some of the weird ionic ones. But now looking at the fourth one, potassium nitride. We said it's ionic. So how do we figure out its formula? What do you got to do first? Okay, so potassium is K and its charge +1. And then nitride is nitrogen and its charge -3, because it's 8 minus group 5 tells you it's a -3. So then to figure out the formula, I just swap them. Okay, so that tells me how many potassium? 3. How many nitrogen? 1. The charge on the nitrogen tells me how many potassium. The charge on the potassium tells me how many nitrogen. But notice there's no number prefixes with covalent. If you're given the name, put the symbol, assign the charge, swap, simplify if you can. But now if I have covalent, PBr3, so first off, what is P? Phosphorus. Okay, and since it's just one, I don't have to put mono out front. Okay, but then I have 3 bromines, so what do I got to say? Tribromide. So remember, if there's covalent, I've got to put the number prefixes in. So see the difference between potassium nitride and phosphorus tribromide. Okay, next one is covalent, but this one I've got the name. Pentanitrogen, what does that mean? 5 nitrogens. Pentanitrogen, 5 nitrogens, and then trihydride, and 3 hydrogens. Make sense? Okay, so that's kind of like going back and forth, going from the formula to the name and the name to the formula. I think in covalent's pretty straightforward. The kicker is you've got to be able to recognize it's covalent. So you look at phosphorus and you find it on the right of the zigzag line, so then you know it's covalent. You look at nitrogen in pentanitrogen, you see it to the right of the zigzag line, then you know it's covalent. And then that dictates that you're going to use number prefixes. All right, so the next one though, I know the next one is Cu, which is what? Copper. So copper, and then 3P. What is P? Phosphide. Right, so it's phosphorus. The beginning part of phosphorus, you just drop the us or us and add IDE. So it's phosphide. Is that it? Yeah. What do I have to do? No, because it's ionic. No number prefixes with ionic. Yes. So the way you remember not to use number prefix, if the first element's a metal, no number prefixes because it's ionic. Okay? If the first element is a metal, no number prefixes. Okay? But because this is copper, iron, and chromium, I have to know what is the charge on my copper. So let's see. Cu3P. I'll just do it really big up there so you can see. I know the charge on the phosphorus is what? -3. Right? Because it's in group 5 and its second element's always negative with ionic. So do you see those are the same? That tells me that the other two are going to be the same. So what would the charge on the copper be? Do you see that the number of copper and the charge on the phosphorus are the same? That tells me that the charge on the copper and the number of phosphorus are the same. So that would be a +2. What's this right here? That would be, if there's nothing, it means it's a, like if there's nothing after, do you remember? That means it's a 1. Right? So this would be a +1. Okay? Do you remember like what you had to do? You had to assign the charges and swap them. This is like doing a reverse swap. As long as the charge on the nonmetal and the number of metal are the same, then I know that the charge on the metal and the number of nonmetals will be the same as well. So it's sort of this reverse. So this, because there's only one phosphorus, that tells me that copper has a +1 charge. So what do I put in between the copper and the phosphide? Roman numeral 1, not 3, right? So remember, that's the second thing that is common. The number 3 in Cu3P tells me nothing about the charge, okay? The 3 tells me it's 3 copper. It does not tell me that copper has a +3 charge. I have to figure out the charge by doing that reverse swap. All right, now this last one's tricky because ammonium. You look at the periodic table, you're like, there is no ammonium up there. Ammonium, though, is what?
Hold on, I got it somewhere.
NH4 with a what charge? +1. Ammonium is a +1. It's NH4 with the positive. It's the only positively charged polyatomic you have to worry about. If it's a polyatomic ion, you know it's an ionic bond, even though nitrogen's a nonmetal. So like that's the only one that doesn't fit that rule. You got to recognize NH4 is the polyatomic ammonium ion, so I know this is an ionic compound. So what's phosphate?
Oh, it's PO -3?
Yep, PO4 with a -3. So ammonium, NH4 plus, phosphate, PO4 with a -3. Now to figure out the formula, how many NH4s do I end up with? I end up not with a -3, I just end up with 3 of them, okay? So you're not going to like, you're going to swap them, but I'm not swapping the plus and minus, I'm just swapping the numbers. So the -3, the 3 of the phosphate, tells me that I have 3 NH4s. Do you see that? So the -3 on the phosphate, so what's in the upper corner, that's the charge. That tells me how many of the ammoniums I have and how many phosphates do I end up with. Only 1. So do I need parentheses? No. So that one's like 2 polyatomics. Most of them aren't that way, but that's an example I wanted to show you. This is sort of like 1, it's an ionic compound because they're polyatomic ions. Anytime you see a polyatomic ion, you know that it's an ionic compound. So what I will do is this one, I will go and put the right answers in and save it as my marked up PowerPoint. See these? I want you to practice these and you can check. So you know that in Moodle, maybe, if I can find it. In Moodle, I post all of these. So here's your Chem 130, section 21. So this is the night class. So in exam two, I've actually been posting the lectures. So like, for example, there's the YouTube lecture from the ionic bonding lecture. There's the YouTube lecture from last time when we did polyatomic naming to covalent naming. So those are the lectures. Right here is what I have listed as Chem 130, Chapter 3, marked up PowerPoint. That's the PowerPoint that I'm writing on. Every time we get done class, I save it. I delete the old version and I upload the new version. So I am going to go and put the correct answers for those slides of practicing the naming. I'm going to put those in this PowerPoint so you can practice them and then come back and check yourself to see, all right, am I picking them up right? So first I want you to make sure that you try them, but then this is where you can find out the right answers. Okay, so all you have to do is go into Moodle, just download that marked up PowerPoint, open it, and then you can see all of the notations that are there. It's just another way to be able to practice it. Okay, so this one, remember, this is what you're going to do first. First thing you want to do is identify, is it ionic or covalent? So you're going to look at the first element in the formula for each, or the first in the name. I just depends on where you got to look at your periodic table. If it's to the left of the zigzag line, you know it's ionic. If it's to the right, then you know it's covalent. So you're going to do that. Always do those first. Then what I would do is I would go through and name the covalent molecules because it's the whole name of the first element, first part of the second element plus IDE, but add the number prefix. So if you have more than one, you've got to list the number, whether it's di, tri, tetra, penta, however many of each element that you have. And then go back and do the ionic ones second. Because the ionic ones, you've sometimes got to figure out what their charge is. Sometimes you got to figure out if it's a polyatomic or not. But that's what I would do first. Identify ionic or covalent, name all the covalents, then practice naming the ionic ones. And I'll post the correct answer so that you can go back and look at them and be like, yes, I got this, or no, I got to practice this one again. Okay, so this brings us into the whole shape polarity part of this chapter. And so when we draw covalent molecules, we like to draw them looking like they're flat. So like when you look at that, that is CH4. It does look flat, but if you look at the little ball and stick structure, you can actually see they're trying to draw it so that it doesn't look flat. In fact, the rule is that every line represents a pair of electrons. So remember, this is 2 electrons, this is 2 electrons, this is 2 electrons. These are 2 electrons. So they're like going back and forth between the carbon and the hydrogen. Well, those 2 electrons are negatively charged and they repel other bonding groups. So the furthest that they can all get away from each other is that 109.5 degrees. So, right, so that is what this ends up looking like. So this is CH4. And so you see it's got like 4 points to it. So from that, that's how it ended up. We can like pass it along as we go. That's where they came up with the name the tetrahedral, because remember tetra means 4. So tetrahedral is sort of like a 4-pointed pyramid. So another way you might see it drawn is it might be drawn looking like this. And so in this one, the carbon's in the middle. There's a hydrogen sticking straight up. There's a hydrogen that's also flat on the board that is coming down to the left. But the 2 that are kind of coming down to the right, they'll use a wedge to show that there's a hydrogen sticking out in front. And they use these dashes to show one that's sticking behind. So if I hold this one just so, you've seen this one. So if I hold this, so it's right like this. Do you see that I can like put this top hydrogen and this one I'm holding like in a line? And this is sticking forward. So this would be the wedge. So when you see this little solid black wedge, that's indicating that it's sticking out in front of the board. So that would be the wedge. And then notice that this one looks like it would be sticking behind the board if this was laying flat on the plane. So that's what this dash, dash, dash is. So just to show you that these are the ones that they would be, like you might see in the book. It's just for them to try and draw it so that it's not so flat looking as the tetrahedral. So this repulsion of electrons for each other, that ended up becoming what they called the Vesper Theory, which is the valence shell electron pair repulsion theory. The whole thing is electron pairs that are part of a covalent bond, that they repel other electron pairs because they're all negatively charged. And you know that similar charges repel each other. So that is how they came up with what they call the ABN formation of a molecule. So in this allowed them to look at any molecule, not just CH4, but anytime you have carbon with 4 single bonds, you're always going to end up with this shape. So they said, well, we can have A. A is going to be the central atom. That is, whatever the atom we're looking at, usually the one that's in the middle. And so you can see with CH4, carbon is definitely in the middle, so carbon is the A. And the second one, the B, is how many groups are connected to it. So how many bonded groups does it have? Well, when I look at CH4, it has 4. So this is bonded groups. And I will tell you, it doesn't matter if there's a single bond, a double bond, or a triple bond. That's all considered a bonded group. So this one has 4 groups connected to it. So we would say that this is AB4. Carbon's the central atom, 4 groups around it. They will always get this arrangement because that is as far apart as those 4 electrons, or sorry, 4 bonding pairs can get from each other. So if I had this, would this have the same arrangement? Carbon with 4 chlorines? Yeah. Would it matter if I had a carbon with a fluorine, a bromine, an iodine, and a hydrogen? It's exactly the same. So the ABN let them look like at a general shape and kind of ignore what the things it's connected to. You're just looking at the central atom and you're asking how many groups, I don't care what the groups are. I don't care if they're single, double, or triple bonded groups, how many groups connected to the atom that's called A, the center. So anytime you see carbon with 4 single bonds, it will always have the tetrahedral. So it doesn't matter if it's a carbon with 4 chlorines or a carbon with a bromine, a fluorine, a iodine, and a hydrogen. They're always going to be tetrahedral because it's AB4. Now, one thing carbon doesn't have is this. N are non-bonding electrons. Carbon doesn't have any because remember that carbon has 4 valence electrons. Every one of its valence electrons participates in a covalent bond. So carbon does not have non-bonding electrons. So you can put yourself a note. Carbon never has any N's. It never has any N values because carbon can have 4 single bonds. But carbon can also have a double bond and 2 single bonds. So you see this arrangement. So these electrons are stuck between the carbon and the oxygen. There's 4 of them, 2 pairs. So these are kind of stuck there, but they're repelled by the 2 electrons that belong to these hydrogens and the 2 electrons that belong between the hydrogen and the carbon here. So they get as far apart as possible, and that creates this little triangle shape. And if I lay it down, you see that it's actually quite flat. Okay, so that's where that term trigonal planar comes from. It's because the carbon, like this, this, and this, what would that ABN be? So we said this one's AB4. Carbon with 4 single bonds is always AB4 and always tetrahedral. What would this one be? How many groups does that carbon have? Okay, so it's AB3. And so if you look at this, you pick it up and you're like, oh, carbon has 3 groups connected. It doesn't matter that one of them is a double bond. That's just considered a group, and a group. Okay? So you can kind of see how these are different. This creates that flat triangle, which is where they come up with trigonal planar. So trigonal, think triangle. Planar, think flat. And again, it doesn't matter if I had those hydrogens. I could have bromines. I could have chlorines instead. If I have a carbon with a double bond and 2 single bonds, it's always going to be trigonal planar. Well, carbon can do one other thing, because carbon can make up to 4 bonds. So carbon can do 2 double bonds. So this is what carbon dioxide looks like. Remember, we drew this one in class. So there's the carbon in the middle. It's got 2 double bonds, one on either side. So these electrons want to get as far apart from each other as possible. Getting on opposite sides of the carbon, this is as far apart as those oxygens can get. They're 180 degrees apart, and that's why this creates a molecule that looks like a straight line. So this is where that term linear came about, because it looks like a little line. And what's its ABN?
ABN2.
Because it has 2 groups.
Oh, AB2.
So it's just AB2, no N. Notice carbon has no N. Ever. It's either AB4, AB3, AB2. So carbon will have 4 single bonds, a double, and 2 single bonds, or 2 double bonds. It could, in theory, have a triple bond and a single. See how that's still AB2? So this is the one that we did that was cyanide. Triple bond to the nitrogen and then a single bond to the hydrogen. But it's still AB2 because it's got just 2 groups connected to it. So the ones that have Ns. Ns are those non-bonding electrons. And there's really 2 atoms that do this. Nitrogen is one. Remember that nitrogen's in group 5. So nitrogen has a non-bonding pair of electrons. Those electrons belong to nitrogen. They don't participate in a covalent bond. Non-bonding electrons actually take up more space. So I think of them as being like this. They move only around the nitrogen. They don't go over to any other atoms. They belong to the nitrogen. Because of that, they take up more space around the nitrogen than the shared pairs. Because shared pairs go out and come back, go out and come back. But these ones stay right where they are. These actually create more repulsion, like a stronger repulsion than bonding electrons do. So here's how this ends up looking. This non-bonding a pair of electrons have this space. So here's my 2 electrons that belong just to nitrogen. And that creates a push, a repulsion of those other 3 bonding groups. And that is why nitrogen, when it's with 3 hydrogens, is not trigonal planar. Do you see that when I lay it down, that blue sticks up just a little bit? You can kind of see it doesn't lay flat on the table like what this one would do. So this one, I can see it's actually flat. Like the hydrogens, the carbon, and the oxygens are all on the same line because this is that trigonal planar. But when I hold this one up, because of the electrons up here, these hydrogens are actually kind of pushed down. And so that's why when I lay this down, that blue nitrogen is elevated above the tabletop because of that repulsion. So this, instead of being trigonal planar, is considered pyramidal. So it's like a little pyramid. It's a little more raised. You always see this with the nitrogen with 3 single bonds. So what's its ABN? How many groups connected? 3. And how many non-bonding pairs? 1. And it's always pairs, not numbers of electrons, but a pair. So that's AB3. AB3N. Okay, and that's going to create that pyramidal shape. It doesn't matter what is on the end of the bonds. These are hydrogen, but I could have put chlorines. I could have put fluorines. So there, it doesn't matter. It would still have that shape. Then oxygen. So oxygen's fanciness is that oxygen has 6 valence electrons. Right? So remember that means that 2 of oxygen's electron pairs are non-bonding. So this group up at the top and this group over here. So now that means they take up their space, they take up their space, and they repel the bonding pairs even more. So when they talk about like bond angles, that's like the angles that are formed. So notice that nitrogen's is like 107, but when you look at oxygen's, it's 104. So that means it's repelled even more. So when I look at a water molecule, instead of those hydrogens going on opposite sides of each other, like what I would see with this, okay? Those oxygens get as far apart as possible because there's no non-bonding electrons with carbon. But when I look at oxygen, I have non-bonding electrons up here at the top, and that pushes those hydrogens so that they can't get exactly opposite sides. They end up with this arrangement, and they call this bent. So oxygen with two single bonds will always make a bent shape. Nitrogen with 3 single bonds will always be a pyramid. It doesn't really matter what they're connected to. They'll always end up with that shape because of the non-bonding electrons. And what would that ABN be? If oxygen is A, how many groups connected?
2.
And how many non-bonding pairs?
What? No, it's 2.
There's 4, right? So two pairs. So this would be N2, right? So remember that each little pair of dots that are not part of a bond, those are those non-bonding pairs. See how oxygen has 4 total or 2 pairs. So in this, I do not expect you to learn bond angles. This is really, this part of this chart is the one that if you have a hard time remembering them, then maybe you want to put that on your note card. AB4 is when you have a carbon with 4 single bonds. AB4, and a good example is CH4, carbon with 4 hydrogens. And it's always tetrahedral, that tetrahedral shape. Then going down, CH2O, carbon with 3 groups connected, is a double bond and 2 single bonds, and that's always going to be trigonal planar. And then the last one, carbon with 2 bonded groups like CO2 will always be linear. Notice that there's no N where carbon is concerned. There's no non-bonding electrons on the carbon, but nitrogen has 1 non-bonding electron. So like NH3, 3 groups connected, 1 set of non-bonding electrons, and that's what creates the pyramid shape. Oxygen with 2 single bonds has 2 pairs of non-bonding electrons, and it'll always end up looking bent. So in those, the ABN, the shape, and then an example. These are all ones we've talked about, all of, I call them like the 5 basic molecules, covalent molecules that we've drawn. You'll see this again in chapter 4, like how carbon, when it starts to form long chains of carbon, how you end up with this kind of pattern. And it's all because carbon with 4 single bonds is always going to have that tetrahedral. So we talk about geometry to a large extent. What?
I was almost finished.
So you don't really have to worry about anything except what I got a box around. So we talk about geometry because covalent molecules have this shape, but they don't actually always share their electrons equally. So this brings up this idea of what they call electronegativity. Electronegativity is the attraction of an atom for its electrons and any electrons that it forms a bond with. So there is this chart. So this chart's like one, if you were in lab last week, like you saw this chart. In this chart, this is really looking at the first 2 groups and the last 6 groups. Doesn't really talk about the transition metals. It's just the first 2 and the last 6. they assigned what they call electronegativity. You don't have to memorize any of these ones because there's really just like a trend. The higher the number, the stronger the atom holds on to its electrons and any electrons that it shares. So looking at this, do you see that metals on the left side have a low electronegativity? They're anywhere from like 0 to 1.5, but pretty low. Look over on the opposite side. Notice like the halogens, fluorine, chlorine, bromine, they are almost twice what you see with the metals. So they say electronegativity increases as you go from left to right on the periodic table. Electronegativity also increases the smaller the atom is. So these are the 4 that have the highest electronegativity on the periodic table. Not that one. Nitrogen, oxygen, fluorine, and chlorine. They all have electronegativities of 3 to 4. 4 is the highest. So if I have a sodium with its electronegativity of only 0.9, if I think about its one little valence electron, its valence electron is like held way out here. Doesn't really pull it in tight. In fact, if sodium can get rid of that one, sodium will become stable like neon. Because it's at 11, if it can drop down and only have 10, that makes it like a noble gas. If I look at fluorine though, in comparison, fluorine would hold its 7 electrons super tight. Like suck them in, okay? So that's not going to give them up. It holds them in really tight. Fluorine is the most electronegative. And so if these two come anywhere near each other, that fluorine will pull the electron away from the sodium. And this is really how you make an ionic compound, right? Because you end up with a sodium that is a positive charge and the fluorine that has 8 valence electrons crammed around it with a negative charge. So that makes sodium fluoride. When the electronegativities are very different, that's when transferring of electrons occurs. But what happens if I have something like a carbon and a fluorine? So if I have carbon, carbon doesn't hold its electrons out near as far as sodium does. They're kind of in between. So they're not way out here, they're kind of here. Because carbon's about 2.5 in terms of its electronegativity. But now if I have a fluorine next to it, fluorine's still going to hold its electrons really close. It cannot pull the electron away from the carbon because they're not that much different. But they can share, right? So we said that they're going to share electrons. So the red carbon electron and the purple fluorine electron are going to get shared, but they're not going to be right in the middle. Instead, what you end up with, the shared pair hangs out over here. So carbon's electron doesn't like spend 50-50. It's more like 80-20. 80% of the time the electron is around the fluorine. 20% of the time the electron is around the carbon. So it's like pulled over to that fluorine closer than it is to the carbon. Do you see that makes the fluorine have more electrons as a rule? The electrons kind of hang out over on that side more, and that is why they say this. They say the fluorine becomes slightly negative. It doesn't form an ion, but it's a little bit negative. That means that the carbon side becomes slightly positive. Just because the negative electrons are more on the fluorine side than the carbon side, they say that is an unequally shared covalent bond, and that creates polarity.
Is this going to be on the test?
Mm-hmm. So you don't have to memorize those, like you don't have to memorize any of the electronegativities. What you have to remember is nitrogen, oxygen, fluorine, and chlorine. Those 4, nitrogen, oxygen, fluorine, and chlorine, and that's why I kind of like, I draw them N, O, F, and Cl, because that's like their position on the periodic table. Those 4, they pull their electrons in and they don't share equally. So if I have one of those four in a molecule and it's relatively small, then I know that that molecule is going to be polar. But now look at carbon and hydrogen. In comparison to these two, if I have carbon and hydrogen, I said carbon has its 4 valence electrons, and its electronegativity is 2.5. Well, look at hydrogen. Hydrogen is 2.1. They're very close. So their electronegativities are much more even. So that means that any shared electrons are going to end up being like right in between. So it's a 50-50 thing. So that means those two electrons spend 50% of the time with hydrogen, 50% of the time with carbon. That makes a much more even distribution of electrons. They go back and forth 50-50. So we have like 50% and 50%. That is a very neutral molecule. That is a molecule that they say is nonpolar. So if there's no nitrogen, oxygen, fluorine, or chlorine, then you know the molecule is going to be nonpolar. If there is only one nitrogen, oxygen, fluorine, or chlorine, then you know the molecule is polar. If there is more than one, now becomes the question of what's the geometry? Where are these atoms? How are they distributed in the molecule? So look at this. So if I have C, and we're going to use like the ones we just talked about. So we're not going to go like with wild and crazy ones. So what would you say with this? We just talked about this. CH4, tetrahedral. Is this polar or nonpolar? Is there a nitrogen, oxygen, fluorine, or chlorine? No, then it's nonpolar. Okay? So if there's no NOFCl, nonpolar. Now, what if I had CHCl, ClH? Yeah. So you look at the molecule. Is there one nitrogen, oxygen, fluorine, or chlorine?
Yeah.
Yes, then it's polar. Because the electrons are going to get sucked towards the chlorine, that side's going to become a little negative. That means the other side of the molecule becomes a little positive. If I have like a green chlorine, I can swap. Can you see when you look at this? So that around that chlorine, that part becomes more negative. Over here, that means this side becomes more positive. So now I create this sidedness to the molecule because the electrons get pulled towards the chlorine. This is a polar molecule. If there's only one nitrogen, oxygen, fluorine, or chlorine, just those four, those are really the big four. So you tell me, here's another one we did, NH3. What would you say, polar or nonpolar? At the top.
It's polar.
Why?
You got an N in it.
So it has one nitrogen, polar.
So that's what you want us to write, one nitrogen polar.
Just like to remember in your head, if I see one NOF or Cl, then I know it's polar. If there's just one, then it's always. So here's another one we did. What would you say?
Non-polar. Oh no, it's polar because it got an O in it.
That's right. It has one oxygen, polar. So if I have just one nitrogen, oxygen, fluorine, or chlorine, it's going to be a polar molecule.
This is a lot of note taking.
So those are all polar. If I have no nitrogen, oxygen, fluorine, or chlorine, then it's nonpolar. So one that we did in lab last week was this, pH3. So what would you say? Why? Doesn't have NOF or Cl. So there's no NOF or Cl, so that's nonpolar. That means that phosphorus and hydrogens, they share their covalent bond, creating this even distribution of electrons, and that's a neutral molecule. Nonpolar molecules are neutral. There's no positiveness to them. So now here's this. Here's a challenge. Here's another one we've done. Right? So this one, CO2.
It's polar.
Okay, so it has an oxygen, so I know that the oxygen pulls the electrons towards it, but then on the exact opposite side, the electrons get pulled towards it. So both of these sides become slightly negative. What is that going to do? They balance themselves, okay? So they balance each other out. So if you have more than one nitrogen, oxygen, fluorine, or chlorine, you have to think about the geometry. Do they balance themselves, or are they all on one side? So this side becomes slightly negative, this side becomes slightly negative, and they say that this is balanced. They balance themselves out, and that is nonpolar. So the only time a molecule is nonpolar with NOF or Cl is they have to have equal numbers of them in the molecule. It's like CO2. Same thing if I took this and I put 4 chlorines on my CH4. I swap those hydrogens. Remember we said chlorines, these are electronegative. But do you see that when I put it like this, do you see like the chlorines are evenly spread around? So yeah, they pull electrons, pull electrons, pull electrons, pull electrons, but I can't turn this and make all the chlorines be on one side. They're evenly distributed. Same thing here. I can't turn this and put the oxygens on one side because of this linear arrangement. So these, which have chlorine, which have oxygen, these are nonpolar because they're evenly distributed around the molecule. So that's the only time nitrogen, oxygen, fluorine, and chlorine will make a nonpolar molecule, is it's got to be evenly arranged. If I take even one of these off and put on a hydrogen, now it's polar. Because now all the chlorines can be over here and the hydrogen side will become positive. So it has to be like uniform looking. That's the only way that you'll see that. I was like, where's my pen? Okay. So there's their example. So if I have two hydrogens, I have a hydrogen and it shares with another hydrogen. Those electrons are like right in the middle, 50-50. So this is a neutral molecule, this is a nonpolar. Nonpolar typically have no nitrogen, oxygen, fluorine, or chlorine. That's like the easiest one to talk about. So CH4. I could also have like CH3, CH3, which we're going to talk about in the next chapter. Nothing but carbon and hydrogen, nonpolar. But this one over here, notice how when they drew that, do you see how that chlorine looks like it's pulling the electron pair closer to it? See how it doesn't hang out with the hydrogen very much? Like this is pretty big compared to this. That's why this side becomes slightly negative, this side becomes slightly positive. That's a polar molecule, HCl. Polar because there's only one chlorine. If there's only one NOF or Cl, you can just say it's chlorine and move on. You don't like have to even think about the shape. But if you have 2, or if you have 3, or you have 4, you got to kind of think about what the shape is to figure out, are they on opposite sides? Are they all the way around the molecule? Or are they all on one side? To figure out if it's polar or nonpolar. So what's the importance between this? Things that are in, here's one that you kind of have to think about, that you have to think about the shape. Because when you look at like CO2, you want to go, oh, well, those balance each other. But when you look at oxygen, you got to remember that oxygen creates a bent molecule. And that's why the side where those electrons are becomes more negative. This side becomes more negative. This side becomes more positive. But this is chemically neutral. So sometimes the shape is important when you're going back and trying to figure it out. but I will just tell you, rule of thumb, only one nitrogen, oxygen, fluorine, or chlorine, it's polar. If there's only one. If there's more than one, then you have to figure out if it's balanced, like CO2, or are they all on one side, which is just increases its polarity. Things that are polar, water, right? Water is like your 2/3 water. So water being this abundant universal solvent in the body. Things that dissolve in water are also going to have a charged nature because water has that charged nature. So like NH3, which is ammonia. NH3, you see that slight positive negativeness. When a water molecule comes up near it, the oxygen of the water molecule is going to be attracted to the opposite way, to the positive parts. So over here, the oxygen will come up and be attracted to any of the positives, so they interact. So you can take ammonia and dilute it in water, and it'll mix. You can shake it up, make a mixture, completely mixes, doesn't separate out. You can do this with sugar. This is why sugar dissolves in water. Sugar is a covalent molecule. It is C6H12O6, nothing but nonmetals and hydrogen. But it can dissolve in water because of all those oxygens, create lots of polar parts to a sugar molecule. So you can take a teaspoon, put it in water, stir it up, completely dissolves. Vinegar, same thing. Vinegar is CH3COOH. So vinegar has two oxygens, but they're on one side. And so that side becomes negative. The other side becomes positive. When you put vinegar in water, you can dilute it and it stays mixed, shake it up, doesn't separate out. So the rule comes up that things that are polar mix with things that are polar. C6H12O6. Yeah, it does have 12 hydrogens. And it's the carbon and the hydrogens. It's C6H12O6. So things that are polar mix with things that are polar. So like when you think about juices, all those things have got to be polar, right? Because water is its sort of base to it. So everything in there is going to be polar, or it might be ionic. Because ionic, things like sodium chloride. You know, if you take table salt and put it in water, what does it do? It dissolves. But it dissolves because the sodium can form sodium ions. Remember we talked about how salts exist as ions? They exist as sodium ions and chloride ions, and that can mix with the water because the water has that slight charged nature. So being charged and slightly charged, positives and negatives are attracted. This is why salts and water and anything that's ionic or polar can mix together. But now we get the non-polar camp. The non-polars. Things that have no nitrogen, oxygen, fluorine, or chlorine in the molecule, or if they are, they're evenly arranged. Things like CH4. Well, CH4, its common name is methane. Methane is natural gas. So it does exist as a gas in nature, but it will mix with other non-polar molecules. Things like gasoline and oil, greases, butter, bacon grease, cooking oils, they all have a mostly carbon and hydrogen makeup, so they are all non-polar. I always think of them as greasy stuff. Stuff that's like greasy. When you get on your fingers, it doesn't wash off easily because it doesn't want to mix with water. Because non-polar molecules do not mix with polar molecules. Non-polar, these are the ones that are like neutral. There's no slight charge nature to them. They're very neutral. And this is kind of like trying to get a magnet to stick to a piece of plastic. Will it? No. There's no attraction, right? Magnets have that slight charge nature. They have like a pole to them. So they'll mix with other things, attract to other things that have that slight charge to them, but not things that are chemically neutral. So chlorine, Cl2. Yes, it's chlorine, but see how they're like side by side. So there's no positive negativeness to it. I always think of like the next time that you cook, if you put oil in your pan, you start heating it up, take and shake some salt in it and look, and you'll see the salt crystals fall to the bottom. They don't dissolve because salt doesn't mix with nonpolar molecules. So salts do not mix in the oil. That's why you had food and you start sauteing, then you add salt. because you have water in your food and the salts dissolve in the water of the food. They don't dissolve in the oil. So it's just sort of an interesting one the next time that you do any kind of cooking. Nonpolar things, though, do like to mix with other nonpolar things. So they kind of make their own little group. This is why, like, there's some recipes will say, like, you melt some butter and then you add olive oil and you mix them together. Well, butter and olive oil, both nonpolar, and they'll mix together. Some engines need gasoline and oil mixed together, like those 2-cycle engine oil. Those have both of them combined. You mix them together, shake it up. They don't separate out. So nonpolar mixes with nonpolar. Polar mixes with polar. Polar can mix with ionic. But polar and ionic, they don't mix with nonpolar, right? So they kind of create this separation. And if you've ever seen oil and vinegar, like Italian dressing, the oil's in the top, the vinegar's at the bottom, and you shake it, shake it, shake it, and as soon as you stop, you can like start to see, and it literally looks like the oil is getting pushed to the top. It's because the water and the vinegar and the spices and the salts, they're in the bottom, and they don't want to interact with oil because the oil's neutral. So they literally just push the oil out of the way. So that's why that rapid separation occurs. Okay? All right, last part of this chapter. Then we can go on to chapter 4. We won't do chapter 4 tonight, but we can get through this. This is the only math in exam 2. It's the only math in chapters 3 and 4. Okay? And so this one, it's about counting. So when we're talking about molecules, remember we're talking about these like super sub microscopic particles. And so the big question was, how do you count that? How do you know what you're measuring out? How do you know it's the right amount of a chemical, whether it's a compound or an element? How do you know how much of them? So they did lots of experiments of trying to estimate how many particles in a measurable amount of anything. So it's kind of like saying trying to give it a like universal counting number. So they came up with the dozen. I'm not really sure why a dozen was chosen, like why they went with 12 and not 10. 10 would have been like, I would have think 10, 20, 30. Instead, no, you got to remember everything by 12s. But they know, so you know a dozen is 12. So if you say I got 12 eggs or I got a dozen eggs, you automatically recognize they're exactly the same thing. So they came with a common counting unit and they called it the mole. Okay, maybe it's because it sounds like it's short for molecule. So maybe that's how that name came about. So 1 mole of anything is equal to the gram formula mass of a molecule. 1 mole of anything is equal to the gram formula mass of any molecule. So they actually started off and they were like, they used carbon as their initial trying to count stuff. So they said, okay, if I have 1 mole of carbon atoms, so it's not even a molecule, it's just C all by itself, it's going to weigh its mass expressed in grams. So if you look at the periodic table, do you see carbon? Carbon, which has 6, the C, and 12.01. Okay, you just take this 12, round it to a whole number. That's the gram formula mass. It's just the formula. It's the mass of carbon expressed as grams. So what if I had 1 mole of water? So water is H2O. So I have to look up 2 hydrogens. How much does each hydrogen weigh? Times 1 gram each. So that means hydrogen would add 2 grams to the total mass, because each one weighs 1. I got 2 of them, so that's 2. How about oxygen? How much does oxygen weigh? 16. So then I'm just going to add 16 grams. This is how much 1 oxygen weighs. So that means that 1 mole of water would weigh 18 grams. All I do is add up the mass of each of the atoms in the formula. That's all. So I could have a really big formula, or I could be talking about like just H2, or I could be talking about Cl2, or I could be talking about CH4. Anything, all you have to do is you just add up the masses of each of the atoms in the formula. So what if I had, like sugar, 1 mole of C6H12O6? How would I find out how many grams of sugar that would be? So find carbon.
12.
I had 6 of them times. How many? In the formula, how many carbons? 6 times. What's the mass of each carbon? 12. Do you see that on the periodic table? So you're just going to take the atomic mass and round it to a whole number. So that would be 72. How about hydrogen? In the formula, how many hydrogens do they have? So C6H12O6, how many hydrogens? 12 of them times 1 each. So that's going to be 12 grams. And then oxygen, how many of them? 6 times. The formula tells me there's 6 oxygens. 16. And that is 6 times 16. 96. And I just add them together. So I just add 96 plus 12 plus 72. 180 grams. So it's the number of atoms times their atomic mass, and then just add them all up. That's what they call the gram formula mass. So Avogadro, who ended up with a number named after him, so there was another scientist that came up and he said, okay, so if this is the gram formula mass, how many molecules is this? So he did calculations and calculations and calculations and calculations. And this was like almost 200 years ago. So, I mean, this was like way back when. He did all of these calculations and he came up with a number that's actually very, very close to what they determined with all the technology that we have. He said, this is how many molecules or particles is in 1 mole.
How do you pronounce that number?
There's a whole lot. 602 with 21 zeros. Okay, that's how many molecules or atoms is present in 1 mole of anything. So 1 mole of water, 1 mole of sugar, 1 mole of carbon atoms. That's how many parts there are to it. So he put this, because this is like way too many zeros, so they put this in the exponent form. So that is 6.02 times 10 to the 23rd. And this is molecules is equal to 1 mole. So really, I can use this like a unit conversion because they're equal. So I can put 1 above, 1 below, 1 below, 1 above. Same thing with the one up at the top. I could say that 1 mole of sugar is equal to 180 grams. So I can use it this way or this way. So this will let me go from moles to grams or grams to moles. The number down at the bottom, if I know molecules, I know how many particles of a substance I've got, I know how many moles. So I can use this just as a unit conversion. The kicker is making sure that you can put it in your calculator straight. That's really like the hardest part for this. So let's do this one. If I have 1.5 moles of H2SO4, anybody need a calculator? Everybody got a periodic table, because that's the other thing that you got. You got a calculator? You came in? You need a calculator?
No.
No. You got a calculator? Periodic table? Do you need one? Okay, so if I have 1.5, if you see moles and you see grams in the problem, okay? If I see moles and grams, then I know I gotta look up the formula mass. Moles and grams, find the formula mass first, no matter what. The formula mass is how many grams in 1 mole. So, if I see So if for this first one, if I see moles and grams, I need to know what they call the formula mass. H2SO4. So H2 means that I have 2 hydrogens, each one weighs 1. So that's 2 grams right there. S, what's the mass for S? 32.07, just rounded to a whole number. So there's the mass of S. And now O4, how much does each oxygen weigh? 16, and I have, that's where this 64 comes in. So 2 hydrogens, each weighs 1. 1 sulfur weighs 32. 4 oxygens, each weigh 16. Add those all up. That tells me how many grams I have in 1 mole. So 64 plus 32 plus 2 ends up being 98. That's the formula mass. So if you see in your problem, if you see grams and you see moles, then you know you need to figure out the formula mass. And all you have to have is the periodic table for it. Take the mass, which is the bigger number on the, for the whichever symbols that you've got, round it to a whole number. I don't know what this is. So now I'm going to solve this just like a unit conversion. What do I know? 1.5 moles of H2SO4 times in a line. So what unit do I put on the bottom? Because whatever I start with always goes on the bottom. What do I want to find? Grams. That goes on top. So the 98 goes in front of the grams because there's 98 grams in 1 mole. Moles gets the 1. So this will always help you make sure you divide when you should or multiply when you should. So notice that moles and moles cancel. So I take 1.5 and multiply it times 98. 140, 147. Do you see why? Do you see that when I set this up, and this is like a 1-step unit conversion, and it won't be more than just 1 step. Because I just have to make sure that I put moles and grams in the right place. When I do this unit conversion, I want moles to cancel and end up with grams. So I write down what I'm given, times in the line. The unit I'm given goes on the bottom. The unit I want goes on top. And then I just have to substitute the numbers based on which formula I'm talking about. So this is H2SO4. And that's where I got the formula mass numbers from. Now, 1.5 moles, how many significant figures? 2. So what do I have to round 147 to? I keep the 1 and the 4. I can't say 15. I'd have to have... It's 147, so it would round to 2 significant figures would be 150, exactly. So it would round up. So that 7 would round my 4 up to a 5. Remember the 0, if there's no decimal, that 0 at the bottom is not significant. It just tells me how big the number is. So it goes from 147, 150 grams would be correct with significant figures. So let's do this next one because we've already got that. So 50 grams of H2SO4 is equal to how many moles? If you see grams and moles, then I want the formula mass. Well, I already got it. I already know there's 98 grams in 1 mole. So what do I put down first? 50 grams. And you can put H2SO4 if you want, or you could just leave it off. I don't care.
Yeah, I'm going to leave that off. That's
That's just telling you what it is. Okay, it's just H2SO4. It's just telling you the formula of this compound. And there's 50 grams of it. So now times what unit do I put on the bottom here? Grams. The unit I start with goes on the bottom. The unit I want is moles. So I can do this in 1 step. So what do I put in front of moles? A 1. And what does grams get? 98. So see that I just used that number? Grams gets the 98, moles gets the 1. This way, grams and grams will cancel. 50 divided by 98. Yep, this is what ends up happening. 0.51020408082 moles. Okay, I can't leave that That's way too many significant figures. How many significant figures in my problem? 50. It's only one because there's no decimal. Remember the 0 at the end, if there's no decimal, that's only one significant figure. So I have to round my answer to one significant figure.
It just be 0.5.
Right? Because remember the 0 out front isn't significant. Zeros out front are never significant. Zeros at the end are not significant unless there's a decimal. So a 50 is only one significant figure. So I have that 0.5. The next number is a 1. So all of that does what?
Go down.
Rounds off. So it'll be a half a mole. Okay, that's my measured number. So I never take like the 98 grams. I don't use those in terms of figuring out significant figure because those are not measured numbers. Those are numbers I got off the periodic table. Okay, so like anytime you do a unit conversion, it's to go back to the measured number. All right, so the last one, and then we're going to quit. And then we can do these tomorrow on Wednesday, and then we'll start chapter 4. So this one, this is not moles and grams or grams and moles. This is moles and molecules. If you see moles and molecules, then you need to use Avogadro's number. You don't have to calculate it. You already know that Avogadro, who studied this his whole life and finally got a number named after him, well after he was dead. Avogadro, he has a unit conversion that's all his own. There is 6.02 times 10 to the 23rd molecules is equal to 1 mole of anything. So I can use it this way, or I could flip it. So I can put molecules on the bottom, moles on top. Either way, molecules always gets 6.02 times 10 to the 23rd. So let's set this one up. What do I know? So 1.5 moles, and you can put H2SO4, you can leave it off. It's just telling you what that thing is. Times in a line. What goes on the bottom?
Mole.
Moles.
It's 1.
Yep. And what goes on top?
6.02 times 23rd out.
Now I want you to put this in your calculator. So these calculators, if you have the old calculator has this button just above the number 7. It's called the EE button. Does everybody see that? The EE button puts your number into the exponent. So the EE is actually times 10 to the. That's the same thing as having to type out times 10 to the. So what I want you to put in your calculator, clear it out first, okay? 1.5 times 6.02. Now hit the EE button. Do you see 2 little zeros showing up in the upper right corner? Those are your exponent numbers. Put 2, 3. So it should look like 6.02 with the little 2, 3. Now hit equals. Did you get 9.03 times 10 to the 23rd?
No.
Did you get 9.03 E23? In yours? Because you have a graphing calculator. Is that what yours looks like now?
No. I got the E. Yeah.
Yeah, so you have the E. So you know that the E means times 10 to the. Right? So you've got to multiply times that answer times 1.5. Yes. So see, that means 9.03 times 10 to the 23rd.
Yeah.
Yep, 6. So I put 1.5 times 6.02 EE23. So if you use the EE, you don't ever have to use parentheses. Like when you do, have you ever done math where you had to put things in parentheses? Nope, this puts parentheses in there. I don't really understand why math teachers don't use this button. It is very helpful, okay? And when you got your answer, do you see that it's 9.03 and then you have a little 2, 3 in the upper corner? That means, mine looks like 9.0323, which means 9.03 times 10 to the 23rd. And yours looks like 9.03 E23, right? Which is saying the exact same thing. So let me see how you put your number in. So 1.5 times 6.02 EE That's 6.02. Yeah. So EE is times 10 to the. Because when you put in 6.02 EE, you get those two little zeros. So all you then are putting in is the exponent. So it like automatically puts the exponent part of times 10 to the for you. Okay? So this, if you have a graphing calculator, that's what you end up seeing is 9.03 E23. That means 9.03 times 10 to the 23rd. If you have the old calculator and you have like that, 9.03, and then this little 23, the little 23 is telling you your exponent value. Okay, so next time we will do these ones, and then we will be finished chapter 3, and we will get started on chapter 4. Yep, so not, well, we'll also talk, you have to go back and do significant figures too, so you should have 2, but we'll talk about that next time.